Let us look at the properties of intersecting secants. Consider two secants of a circle intersecting each other inside or outside of the circle. Corresponding to any one of the two secants, we have two line segments, each of which has one end point. The point of intersection of the two secants and the other end point is a common point of the secant and the circle. In this figure, the secant AB intersects the secant CD at the point P, and the points A, B, C, D are on the circle. The two line segments corresponding to the secant AB are segment PA and segment PB, and corresponding to the secant CD are segment PC and segment PD. A rectangle formed by two line segments whose lengths of adjacent sides is equal to the lengths of the two line segments respectively. A rectangle formed by segments PA and PB is shown here, where PA is equal to LM and PB is equal to LN. Note that instead of two intersecting secants, we may also consider a secant and a tangent of the circle intersecting outside of the circle. Intersecting inside the circle is not possible. Then the two line segments corresponding to the tangent coincide, and we get only one line segment corresponding to the tangent, namely the line segment from the point of intersection to the point of contact of the tangent. In the figure, the line segment corresponds to the tangent PT is segment PT. Now, the rectangle formed by one line segment is a square with the length of every side equal to the length of the line segment. Theorem: if two secants of a circle intersect inside or outside the circle, then the area of the rectangle formed by the two line segments corresponding to 1 secant is equal in area to the rectangle formed by the two line segments corresponding to the other. Given secants AB and CD intersecting in point P, to prove area of rectangle formed by sides AP and BP is equal to area of rectangle formed by sides CP and DP, that is, AP into BP is equal to CP into DP. Construction: join AC and DB. Proof: suppose the point P is in the interior of the circle. Consider triangle PAC and triangle PDB. Angle APC, angle BPD form vertically opposite angles. Angle CAP and BDP are inscribed in the same arc. Therefore, triangle PAC is similar to triangle PDB by angle-angle test of similarity. Therefore, AP upon DP is equal to CP upon BD, as corresponding sides of similar triangles are proportional. Therefore, AP into BD is equal to CP into DP. Suppose point P is in the exterior of the circle as shown in the figure. Now consider triangle PAC and triangle PDB. Angle PAC plus angle BDC is equal to 180 degrees since they are opposite angles of cyclic quadrilateral. Mark this as 1. Therefore, angle PDB plus angle BDC is equal to 180 degrees since they form linear pair. Mark this as 2. Therefore, angle PAC is congruent to angle PDB from 1 and 2. Angle APC is congruent to angle DPB since they are common angle. Therefore, triangle PAC is similar to triangle PDB by angle-angle test of similarity. Therefore, AP upon DP is equal to CP upon BP, as corresponding sides of similar triangles are proportional. Therefore, AP into BP is equal to CP into dp. Hence, if two seconds of a circle intersect inside or outside the circle, then the area of the rectangle formed by the two line segments corresponding to 1 secant is equal in area to the rectangle formed by the two line segments corresponding to the other. Let's look at another theorem. If a secant and a tangent of a circle intersect in a point outside the circle, the area of rectangle formed by the two line segments corresponding to the secant is equal to the area of the square formed by the line segment corresponding to the tangent. Given, a secant through the point P intersects the circle in point A and B. Tangent drawn through the point P touches the circle in point T. We have to prove PA into PB is equal to PT square. We will use concept of similarity to arrive at the result, for which we require triangles. So, let us join BT and AT. Proof. In triangle PTA and triangle PBT, angle PTA is congruent to angle PBT as these angles are formed in the alternate segment. Angle TPA is congruent to angle BPT as they are common to both the triangles. Triangle PTA is similar to triangle PBT by angle-angle test. PT upon PB is equal to TA upon BT is equal to PA upon PT as corresponding sides of similar triangles are proportional. As the first and the last ratio have PT, so let us consider these ratios. Therefore, PT upon PB is equal to PA upon PT. PA into PB is equal to PT square by cross multiplying. Hence, if a secant and a tangent intersect in a point outside the circle, then the area of the rectangle formed by the two line segments corresponding to the secant is equal to the area of the square formed by the line segment corresponding to the tangent. Let us look at the examples. Example 1. In the figure, secant AC and secant AE intersect in point A. B and D are points of intersection of circle and seconds respectively. If CB is equal to 5, AB is equal to 7, EA is equal to 20, determine ED minus AD. Solution. Using property of intersecting seconds, we get AB into AC is equal to AD into AE. 7 into 12 is equal to AD into 20. 4.2 is equal to AD. ED is equal to AE minus AD is equal to 20 minus 4.2 is equal to 15.8. ED minus AD is equal to 15.8 minus 4.2 is equal to 11.6. Example 2. Let the circle of radius 10 with center O pass through two adjacent vertices of a square. A tangent segment to the circle drawn from a third vertex B of the square ABCD is twice the length of the side of the square. Find the side of the square. Solution. Let the side of the square ABCD be x. Then BM is equal to 2x. Extend the line segment AB to intersect the circle at point K. Then BK into AB is equal to BM square. BK into x is equal to 2 square. BK is equal to 4x. Hence, AK is equal to 3x. Since angle KAD is equal to 90 degrees, KD is a diameter of the circle. In right-angled triangle KAD, AD square plus AK square is equal to KD square using Pythagoras theorem. X square plus 3x square is equal to 20 square because radius is equal to 10. 4x square is equal to 400. X square is equal to 100. Therefore, x is equal to 10. Thus, side of the square is 10. Let us solve exercise 2.5. Number 1. A tangent segment PA is touching a circle in A and secant PBC are shown. If AP is equal to 15 and BP is equal to 10, find BC. Solution. Tangent AP and secant BC intersect in point P outside the circle. PB into PC is equal to PA square by the property of intersecting secant and tangent. Substituting values of PA is equal to 15 and PB is equal to 10, we get 10 into PC is equal to 15 square. Therefore, PC is equal to 225 upon 10 is equal to 22.5. Therefore, PC is equal to 22.5. PC is equal to PB plus BC as point B lies between C and P. Substituting the values of PC is equal to 22.5 and PB is equal to 10, we get 22.5 is equal to 10 plus BC. BC is equal to 22.5 minus 10. Therefore, BC is equal to 12.5. Number 2. Point M in the interior of the circle is the point of intersection of two chords AB and CD of the same circle. Show that CM into BD is equal to BM into AC. Solution. Draw segment AC and segment BD. In triangle AMC and triangle DMB, angle AMC is congruent to angle BMD since they form vertically opposite angles. Angle MAC is congruent to angle MDB since they are inscribed in same arc. Therefore, triangle AMC is similar to triangle DMB by angle-angle test of similarity. Therefore, CM upon BM is equal to AC upon DB as corresponding sides of similar triangles are proportional. Therefore, CM into DB is equal to BM into AC. That is, CM into BD is equal to BM into AC. Number 3. Two circles intersect each other in 2 points A and B. Segment AB is the chord of both the circles. Point C is the exterior point of both the circles on the line AB. From point C, tangents are drawn to the circle touching at M and N. Prove that CM is equal to CN. Solution. CM is a tangent segment and CBA is the secant. Therefore, CM square is equal to CB into CA by the property of intersecting secant and tangent. Mark this as 1. Similarly, CN is a tangent segment and CBA is the secant. Therefore, CN square is equal to CB into CA by the property of intersecting secant and tangent. Mark this as 2. Therefore, CM square is equal to CN square from 1 and 2. Therefore, CM is equal to CN by taking square root on both the sides.